Hello, my name is Fromsa. This is a presentation on cryptography algorithms, more just an introduction to cryptography and the algorithms behind it, and specifically focusing on post-quantum cryptography. So what is cryptography? Cryptography is the art of keeping information hidden in plain sight, and what that means is keeping information private from peeping eyes or people who wants to spy on it, see the information, and figure out what it is. How do we do it? We use functions to take a given information and change it into something that means nothing. It has no meaning. It's just gibberish until it's decrypted back to its original plain text. Uh, why do we do this? It's just the need to keep information private. For example, one of the first cryptography machines is like the Enigma machine by the Germans, the Nazis, during World War II, where they wanted to share information between their soldiers, but they did not want the Allies figuring it out. And another reason we would use it in the civilian space is to keep things like credentials private, keeping cards like your identity private when sending information across the internet. Just in general, since the internet has come out, there's been a lot more need for cryptography than there was prior to the internet. There are three types of cryptography: symmetric key cryptography, asymmetric key cryptography, and hash functions. So symmetric key cryptography is the simplest form of cryptography to understand, at least the algorithms behind it. It uses the same key to encrypt the data and decrypt the data. So the sender uses one key to encrypt plain text into ciphertext, and you also have to have the receiver, the person that's getting the message, have the key so that they can use the same exact key to decrypt the cipher back into readable plain text, right? This is generally not affected as much by quantum computers because it doesn't. Well, quantum computers are efficient at breaking the relationship between private and public keys, and asymmetric key cryptography does not use. I mean, symmetric cryptography does not use private or public keys. It's the same exact key to decrypt and encrypt the information. Some popular algorithms behind it are AES and DES, but I won't be going into detail of that. I'll be talking about more asymmetric algorithms. So what are hash functions and how do they work? Hash functions are functions that convert input into an output that is exactly the same length and is a one-way thing so that it cannot be reversed back to for you to get the original information that was input. And the reason why it's unreversible is because it loses information or it can add in information, right? So with hash functions, if you put in the same exact value, you'll get the same exact output no matter what. So you can see why this is useful when storing information that you don't want to have it stored in plain text. Things like passwords. If you have a giant server that's just storing passwords for your clients or the people that are going to be using a certain server, right? You don't want to store those things in plain text because if someone gains access to that, then they'll know the password and they'll easily be able to access it. So you can use hash functions to store these things because as long as the person inputs the exact value, it will always output the exact thing, and you can just compare the hashes at the end to see if the passwords match. And they are one way because they either add information in or they take information out. For example, they add information in if you input something that's a single bit and you're inputting it into like a SA256, it will add the other bits, but it'll be very different, right? And if you take something that's like a gigabyte long and you input it into this function, it will still give you something that's 256 bits long. So now you're throwing away like an entire gigabyte's worth of information, and you're ending up with just 256 bits to represent the entire file. And the value of hash functions comes from the fact that they're irreversible and they're deterministic. And this makes it really good to store things like I said, passwords, or to tell you if something has changed, right? So this is used in Yeah, another area it's used in is forensics. If you want to make a bitstream copy of a disk, you can make the bitstream copy of a disk, and then you can make a hash of the original disk, and then compare the hash to the hash of your bitstream copy, which should be the exact same. And later on, you'll use that in court to show that these two disks are the exact same in terms of the information that they hold. So hash functions are valuable in a lot of different places, but they're not going to be discussed in the rest of this presentation because they're not as affected by quantum computers. They're resistant already. So asymmetric cryptography is what's going to be most affected by quantum computers, and it's also going to have the biggest impact in general on current day infrastructure of how the internet is set up, because we use a lot of asymmetric key cryptography to keep information hidden. So, but we don't necessarily use asymmetric cryptography at all times because it's expensive to do it. It takes a lot of compute power to decrypt something, even if you already have the key, and to encrypt something, even if you do have the key to encrypt it with it, right? So we use asymmetric to get the original keys to pass along. For the symmetric cryptography, you get the key passed through asymmetric cryptography, and then you use the symmetric key cryptography once you have those things passed. Once they both have a key, they can use that to encrypt the information, and it'll be a lot faster and a lot smoother. But modern day functions are very vulnerable to, I should say, modern day algorithms are very vulnerable to quantum computers, and the most common algorithms are RSA, etc., and they're all breakable by quantum computers, and that's why we have, um, and that's why we'll discuss asymmetric cryptography in the rest of this presentation. So as of right now, there is no quantum computer that's big enough to decrypt any modern day algorithm that's used for asymmetric key encryptions. But in the future, there will certainly be, well, I don't, not certain, but somebody will probably make a quantum computer big enough to decrypt these things. And it's a problem that we need to get ahead of, because you can save information. You can just keep downloading a whole lot of information as it's traveling across the internet, and then decrypt it later. So this is a problem for governments and for like organizations that are really powerful. But for the normal day, for the everyday person, it doesn't necessarily matter as much. Um, so, like I already stated, quantum computers don't affect symmetric cryptography as much as they break asymmetric key cryptography, right? And that's why, with the foundation of the internet being based on asymmetric key cryptographies, if they break that, then the security of the entire global internet infrastructure is at risk. But they don't exist yet. But you still need to get ahead of them because of the people that are downloading all the data to eventually, hopefully, decrypt it once they have quantum computers strong enough to decrypt it. Okay, so NIST has recently announced its decision on the algorithms that it's chosen for the future of like the post-quantum future. The four algorithms, well, three of the four algorithms use something called lattices, and that's going to be the algorithm we discussed today. And learning with errors, this is another one that we'll be talking about at the end. So a lattice is essentially just a whole lot of dots or points that are repeating patterns, and they're built off of bases. But this is the actual definition of it. But I think that's easier to understand once we actually make a lattice based on bases on a 2D plane, and then you can see how that scales up through dimensions. Because while in reality there's 3 dimensions, in mathematics you can define the dimension to be whatever you want. So that will be what's used to increase the complexity of the problem to a degree where even supercomputers or quantum computers will have issues solving these things, and that'll be the hard problem that's used to encrypt information so that it can't be as easily decrypted. So a lattice can be formed off of a basis that is a super easy basis to solve. For example, we can use a basis that is 1, 0, and 0, 1. these bases are just vectors, and when you form a lattice, you take two vectors, leave the origin point, however way you want to leave the origin point, and then you put a dot at the end of the vector. So in this case, let's say the origin point is just the one in the middle here. Oh, I'm sorry, unfortunately you guys can't see the arrow that I'm pointing at, but let's just say, just pick an origin point, you leave it, go up 1 and 0 in any other direction, you put a dot there, and you use the other, you can use the A2 to go sideways, put a dot, oh sorry, flip it, A1 to go sideways, put a dot down, A2 to go up and put a dot, and you can build this entire structure off of just these two simple bases. And that's the thing about bases, is that you can have a simple basis or a basis that's really difficult to build a structure with. And that's what we'll talk about on the next slide. So as we alluded to earlier, you can have one lattice structure be formed out of multiple bases. So the other base we were using, which was just O1 and 1O for the two vectors, is super simple to construct with those two bases, right? You can build the entire grid. You just go up 1, sideways 1, and it's super easy to go in any direction you want to go in. But that's why it's considered a good base, because it's super easy to figure out and choose a direction you want to go in. A bad basis is one that's kind of pointed out right here with these two arrows, or lines I should say, and ending in these 2 points. These are really difficult to build a basis with because the angle difference between them is almost, well, 0. The closer it is to 90 degrees between the two vectors that you're given, the easier it is to build your lattice structure. And the less the angle is, the closer to 0 it is, the more difficult it is to build a lattice structure with them, because let's say you want to go just one to the left, for example, of the arrow of the vector that's at the top, the one that's higher. If you want to go just one to the left, you have to go down multiple times and then go back up a few times to get to that point. But if you had a simple vector or a good basis, you could just go negative of A2 and you would end up, no sorry, negative of A1 and end up at the point you were at. So the hard problem that is specifically used to build encryption platforms on this lattice idea is that given a bad point or given a bad basis for the lattice, it's really difficult to get to the exact point you want to get to. So for example, if you were asked to get to the blue dot on this with these two vectors, it'd be a lot more difficult than getting to the same to the blue dot given the good basis. So that's what the hard problem is, and you can make this more difficult because I mean you can get lucky and end up on the blue dot even with a bad basis, but you can make this problem significantly more difficult if you don't put the the coordinates that you're asking about, like the blue dot for example, on the point. Instead you put it next to or close to a point and ask the question of what is the closest point on this lattice to this coordinate that I'm specifically giving you, and that becomes significantly more difficult to solve for than just like asking exactly to get to this point, because you could end up on the point, but with the point and then confirm that, oh okay, so I've gotten to, this is the exact point that you're looking for, this is how you get to it. But if you were to ask the question of what's the closest one and use that for your encryption, the person would have to build out the entire lattice to be able to give you an answer of which point is the closest one, but they have the bad basis to do it, so it would be significantly more difficult than the person with the good basis, which would be the private key, to find the point closest to the lattice or closest onto the dot. And the point of the sorry, so the point here is that like you're not necessarily asking the person to build out the entire lattice, but if you were to give them the question of what's the closest one here, they would have to build out the entire lattice to be able to give you the answer. And with the bad basis, it's significantly more difficult than it is with the good basis, and that gives you the easy problem and the hard problem, making it good for public key, private key type of encryption, or the asymmetric type of encryption. So bases on lattices in 2 dimensions are really easy to understand, but if we can intuitively see the answer in the 2 dimensions, you understand that like a supercomputer would be able to solve these things pretty much in an instant. So a 2-dimensional lattice is useless for security purposes at least. But for cryptography and security, they don't rely in 2 dimensions because math is fluid. You can just add however many dimensions as you want, unlike in reality, which is pretty much limited to 3 dimensions. The lattices are built up of bases with over 1,000 dimensions. All right, and that makes it almost impossible to move through the lattice how you want to move through the lattice unless you have the good basis. So let's say you go down in 1 dimension, you're going potentially the wrong direction in the other 999 bases, the other 999 dimensions, and that makes it really difficult to be able to say with certainty this point is the point that's closest to the point that's being asked, right? Like unless you build up the entire lattice structure, it's almost impossible to answer these questions, and that's what makes it really good, because even quantum computers aren't any better at solving these problems than classical computers are, making it a really secure thing for the future. So for more information on lattices and bases, I would suggest going to this PDF. It was a very good read. It's 100 pages. It's very mathematical and it gives you a lot of information, but it's a good place to learn more about lattices and bases. I didn't cover a lot in this. So yeah, if you were looking for the actual mathematical stuff, you would go to this and it would pretty much cover everything you need to know. That being said, thank you for watching my video. I appreciate it.